Methanol to olefin is a catalytic process converting methanol into vital olefins like ethylene and propylene, employing zeolite catalysts. In a dual cycle mechanism, methanol is first dehydrated to form an initial olefin in the primary cycle, followed by a secondary cycle involving reactions like cracking and isomerization to produce ethylene and propylene. MTO utilizes abundant and renewable feedstocks such as methanol from natural gas or biomass, making it an economically attractive option for olefin production. Despite challenges in catalyst stability and selectivity, MTO shows promise in diversing feedstocks and enhancing the sustainability of olefin production. The methanol to olefin process is the catalytic conversion route transforming methanol or dimethyl ether into ethylene and propylene through a dual cycle mechanism where zeolite catalyst plays a pivotal role. The typical process conditions vary but often involve high temperatures ranging from 400 to 600 degrees Celsius and moderate pressures around a few atmosphere. The inner composition, primarily methanol or dimethyl ether, influences reactor conversions and selectivity. Selectivity towards ethylene and propylene is intricately linked to catalyst type, acidity, and crystal structure. The process aims to balance maximizing olefin production with controlling undesired byproducts. MTO synthesis underscores the importance of ethylene and propylene in chemical and polymer manufacturing. Challenges including catalyst deactivation and control of product distribution have prompted ongoing research into innovative catalyst designs and process optimization. Overall, the literature provides a comprehensive overview of the MTO process, its technological advancement challenges, and potential contributions to sustainable olefin production. Now let's move on to the synthesis rule. The MTO process is a dual cycle mechanism that involves two reaction cycles which are the primary and secondary cycle. In the primary cycle, methanol or dimethyl ether undergoes dehydration on the surface of zeolite catalyst. This step leads to the formation of an initial olefin, commonly ethylene or propylene. In the secondary cycle, some of the produced olefins undergo secondary reactions such as cracking, where the primary olefin generated enters the secondary cycle where it undergoes cracking. This involves the cleavage of carbon-carbon bonds resulting in the production of olefinic fragments. Isomerization reaction may occur leading to the changes in the molecular structure of the olefinic intermediates. Hydrogen transfer reaction can take place influencing the final composition of the product mix. The combined effect of these secondary cycle reactions results in the formation of the mix of ethylene and propylene which are the desired secondary products. The preferred reactor for the methanol to olefin process is the fluidized bed reactor, a traditional and widely chosen option. Characterized by a stationary catalyst bed, it stands out for its operational simplicity and ease of design. Its popularity is on the rise, driven by improved heat management and simplified catalyst regeneration. Operating with a fluidized catalyst state enables continuous operation and efficient heat transfer, enhancing the overall effectiveness of the MTO process. In this part, we will discuss about the multiple reaction. In the primary reaction of methanol to olefin process, intricate chemical reactions transform ethanol or dimethyl ether into crucial light olefins, predominantly ethylene and propylene. The primary reactions involve the conversion of methanol to dimethyl ether with a corresponding rate law as shown in the slide. Subsequent transformations include the conversion of methanol or dimethyl ether to ethylene, which gives the rate law as shown, and the conversion to propylene with the shown rate law. Assuming elementary reactions, these rate laws are established based on the stoichiometry of each process, providing essential insights into the kinetics of the MTO reactions. Additionally, the methanol to olefin process includes the side reactions such as formation of butenes and higher olefins. This occurs through the conversion of methanol or dimethyl ether. The rate law for the formation of butenes is represented as shown in the slide, reflecting the dependence on the concentration of methanol or dimethyl ether.
So here is our reactor system. We use PBR for this project, and here is our inlet pipe for methanol to get into the reactor. And next, this is our recycle pipe where methanol is recycled back into the reactor. And lastly, here is our outlet pipe where the product is get out from the reactor. So basically, the sizing that we use in this project or in this design is basically from the industrial industrial size.
So hi, I am Akmal. So I will be continuing with the calculation part. So how we do calculation, we need to do to find the yield and also the selectivity. So firstly, we find the value of the reaction kinetics through the three different research papers, and then we list out all the rate law and use the relative rate law to find all the net rate law. In order to find the selectivity and also the yield, we need the rate law value. So how to find the rate law value? We first finding the concentration of A, which is the methanol, and concentration of B, which is the dimethyl ether. So how we find it? Basically, we do the stoichiometric table. We list all the species, symbol, fit changes in total, and then later we get the equation for the concentration that will be later calculate to find the Ca on the whole Cb to get the rate law. So next we need to find the value of the Ca naught. So how we do this is basically we use the project description where we need to produce 100 kilogram per day of dimethyl ether. So we use that value with the conversion of zero point 0.9 and we get the value of Fa naught, and next we move on to finding the V naught and also calculate the Ca naught by using the Fa naught multiplied by V naught. So after finding the CA naught, we calculate the CA and also the CB, and then we find all the value for the red law product. So our main product is basically the dimethyl ether, and also the side product is olefins, which is C2H4 and also C3H6. As you can see, the red law of C2H4 and also C3H6 has is the same value as they both are olefins. So now we have all the information needed to find all the selectivity and also the yield. So starting with the instantaneous selectivity, we use the formula of R desired product over R undesired product. We obtain the value of 5.6938, and next the overall selectivity by using the formula of flow rate of the desired product over the flow rate of the undesired product and obtain the value of 0.111. And lastly, the yield of each product, starting with the yield of the desired product by using the formula of R desired product over the limiting reactant, we obtain the value of 0.41, and also the yield of C2H4, same goes with yield of C3H6, the same value 0.03604, as they both are olefins.
We use Polymath to run the same calculation with the same input variables as my teammate introduced before. The important outcomes are overall selectivity, denoted as S, instantaneous selectivity, denoted as SDU, and the U denoted as Y in the programming, which we can also see the numerical answer in the Polymath report. The calculated numerical values are the same as the result we got from the Polymath. Then we use Python to simulate conversions from zero point 0.1 to 1 with an interval of zero point 0.1 to get different selectivity. To begin our Python coding, we need to use some pre-built modules. For example, we import PyLab from the matplot library as PLT to generate insightful graphs. Next, we import NumPy as NP, a numerical computing library that empowers us with advanced capabilities for efficient data manipulation and analysis. The coding at the bottom right are used for the graph plotting, which we need the coding for the X and Y axis, the title, the color, the marker, the grid, and etc. These are the results we obtain after we run the Python programming. The different inputs of conversion change the instantaneous selectivity, which is shown on the left side, and we also obtain a graph of instantaneous selectivity versus conversion, which also shown at the right side of the slide. This coding is similar as the last coding, but we aim to get different yields for each product by inputting different conversion. There are three products which are B, C, and D, which have been mentioned in the coding. The results of different inputs of conversion with the yield of each product are shown on the left side. We also obtain a graph of yield versus conversion, which shown on the right side. The blue line and green line that represents the yield of C and D respectively is overlapping as their calculated numerical values are the same. This is because that they are the same group as the alkene group, and this has been explained by my teammate in the calculation section.